All right. With that said, which of the review questions do you want to go over? Which of the review questions? Number 2. All right, let's look at review number 2. Now, these are KSP problems. We didn't have time to go through KSP because the test and such are not. All right, answer the question of the solubility. Now, let's actually, before we do this, let's just kind of create a place for some notes. We didn't get a chance to talk about KSP. Let's talk about KSP for just a moment, and then we'll go back and do review 2. So let's kind of pause here and talk KSP. SP stands for solubility product. Remember, this is a weird thing. This is studying the solubilities of insoluble compounds. The solubilities of insoluble ionic compounds. Got that? That's kind of weird. It's the solubility. This is what KSP is studying. So if you've got calcium carbonate is, from our Nakalnoso rules, from our solubility rules, says that this is insoluble. So calcium carbonate, we remember double Ca2 positive plus CO3, 2 negative, and this is a solid. So from our Nakalnoso rules, we've learned that this right... Oh, here I am talking, and you guys should tell me that I forgot to unblanket. The calcium carbonate right here is going to break apart. So the solubility of insoluble ionic compounds. So that's what this is. And we have S's, and there's a KSP value. KSP would be equal to the concentration of the calcium ion times the concentration of the carbonate ion. And in this case, the appropriate powers, but the appropriate powers are 1 and 1 in the example that I just gave. So if that kind of rings a bell for you, that'll kind of help us with solving these problems. If you end up with the KSP problem in the AP exam, then you know it's going to be a big mathematical problem. All right. So today I'm kind of I'll say that. All right, Stephen. All right. Review number 2. Let's look at number 2. It says, answer the following questions regarding the solubility of the chlorides of silver and lead. At 10 degrees Celsius, 8.9 grams of silver chloride will dissolve in 100 mils of water. Write the equation for the dissociation of AgCl. So that'll be AI. AgCl dissociates into Ag positive plus Cl negative. That's it. Now remember, on an AP question, and these are all old AP questions, the first question is invariably an easy question. Don't outthink the question. It should be relatively easy. They're going to get harder. Don't get me wrong. It's going to get hard. So what's the second question? It says, calculate the solubility in moles per liter of silver chloride in water. What they're asking for, they gave you that if you take 8.95 grams times 10 to the minus, it looks like 5th grams, you want to dissolve that in 100 milliliters of water, or I'm going to say in 0.1 liters, and that's grams of AgCl. If I want to find the solubility, folks, all they're asking you is to find its molarity. So you say grams of AgCl to 1 mole of AgCl. Now, I think if I recall this, isn't this 143.5? From my recollection, or did they give it to you? I just am remembering it from somewhere. So you get your calculator out. And so when I got this all worked out, I get 6.2, and how many significant digits? You can keep 3 significant digits. 6.24 times 10 to the minus 6 molar. Because of the 8.95. Now you got to watch your sig figs, because on the test they can take away points. So I'm going to try and be good about that. Alright, that's now. The next question probably is what's the KSP? So it is. Calculate the value of the solubility product constant. But this is the molar solubility, so this is equal to what, as we've learned? S. Alright? And silver chlorides break down into S and S, right? So the KSP would be equal to the concentration of the silver ion, which is S, times the concentration of the chloride ion, which is S. This will be S and S, or S squared. And if this is S, it will be equal to 6.24 times 10 to the minus 6 moles per liter squared. and that equals 3.89 times 10 to the minus 11. No units on KSP, or NK, equilibrium constant or whatever. Good? Is that ringing bells now? But you got to be able to do this like totally on your own come May 15, right?
How does it work? Like, is there another, proctor in the room or something?
You'll have a proctor in the room. I don't know. It is not allowed to be me. So I don't know here at Woodland Park how it's done. We had a counselor at my old school who would run the test. So you guys all be locked in a room with one proctor, and he or she will take care of you. It's like taking an ACT. They'll tell you, stop, put your pencil down. It's going to feel kind of like an ACT. Yeah, we're going to go over test strategy on one day. I'm going to give you an actual old AP exam. There is a one modification or two modifications to these tests, but we'll talk about it. So don't worry about that. That is not a particularly big issue just yet. This would be one of the questions. And honest, this question you would be allowed to have probably 20 minutes. Now there is some variation, but that's your budgeted time. All right, we did letter A. Now review for question B, right? All right, at 25 degrees Celsius, the KSP for lead chloride is such and such, and silver chloride is such and such. By the way, this is a different KSP for silver chloride than we just calculated because we're at a different temperature. Do you notice that? If 60 milliliters of sodium chloride is added to 60 milliliters of lead nitrate, will a precipitate form? Assume the volumes are additive. Show calculations to support your answer. All right, with this chemical lead chloride. Lead chloride, always write out the reaction. Good call, right? Pb2 positive plus Cl minus. And now what's wrong with this? What do I need to do? I need to put a 2 by the chloride. I know the value of the KSP. They gave this to me to be 1.6 times 10 to the minus 5 moles per liter. We're going to put in there 60 milliliters of 0.0400 molar NaCl, and we're going to put in there 60 milliliters. I like that, of 0.0300 molar lead nitrate. What do we care about excuse me, in terms of the sodium chloride? You care about the chloride because we're working with lead chloride. And what do you care about with the lead nitrate? Just the lead. Now I want you to notice here, both of these, in the chemical formula, there is one chloride, and also in the lead nitrate, one lead. Sometimes it might have a 2, like Pb2, something like that. In that case, you have to double these numbers. But what you need to do is find the molarity of the chloride. Now we can do this in our head, okay? You could do M1V1 equals M2V2. That's essentially what we're going to do, but the concentration of the chloride will be what? Can anybody kind of figure it out? Since we're putting 60 milliliters with 60 milliliters, you are doubling the volume, so what happens to the concentration of the chloride? It's cut in half. So what's half of O4? It's 0.0200 molar. And the concentration of the lead, same ballgame, 2 Pb2 positive, that's going to be what? Half of 0.03, 0.015. Now, does everybody know how I did that? I'm doing this kind of quickly in my head. If you need to plug it in to M1V1 equals M2V2, but since you're doubling, because your volume here would be 60, and your volume here would be 120, right? And this is 0.04, and trust me, this X right here will be 0.02. They're going to try and not make it so. They're not going to use 32.5 milliliters and 63.8. In that case, you've got to plug it into the M1V1. But typically, they realize that if you understand this, you can plug it in to go the long way, then that's fine. But if you can, yeah. So that's it. Now, but that's not the answer. The question is are we going to make a precipitate? Remember, to do this, we have to calculate what's called the QSP. The QSP has the same formula as the KSP, but then we're going to compare it to the value of the... And so what's the QSP formula? Going to do this, it'd be the lead times the chloride, and a little tricky, I've got to also do it with the chloride. I've got to square it because you see there's a 2 right here, isn't it? So the lead will be 0.0150. I'm trying to keep all my significant digits because I'm pretending this is an AP exam. The chloride will be 0.0200 squared. So when you multiply those out, I don't know what you get, 0.015 times 0.02 squared, I get 6.0 times 10 to the minus 6th. Now what do I know, what do I do with this right here? I compare it right up here to the KSP. So the QSP is what? Is it bigger or smaller? It's smaller than the KSP, isn't it? Will it precipitate form? No. If the QSP is greater than the KSP, you will make a precipitate. If the QSP is less, then it will not make a precipitate. Now I would probably at this point write a sentence and say, since the QSP is smaller than the KSP, no PPT will form. You can use the abbreviation, by the way, PPT on the AP exam. There's no chemist in the world who wouldn't know what that meant. You don't have to write the whole word out, precipitate. If you want to, that's fine. Good? Alright, that's basically BI. Now, we got another question. Calculate, big question, isn't it? BII. Calculate the equivalent value of PB. Alright, first of all, you know what I'm going to do? I don't even read the question, but I'm going to redo. I'm going to recopy this. I got a lead question, so I'm going to write lead chloride goes to lead 2 positive plus 2 Cl minus. You're going to probably have to write it several times. They're trying to find the concentration, looks like the lead, so this is going to be my question mark, of a saturated lead chloride in which 0.25 moles have been added to 1 liter. So what's the concentration of the chloride? It's 0.25 molar. It's 0.25 in a liter, right? So 0.25 moles in 1 liter. If they'd have said in 2 liters, you'd divide by 2. Alright, so now we're going to have the KSP, if you call KSP, is equal to, they gave us a number, I lost it in my brain, 1.6 times 10 to the minus 5. That's equal to the concentration of the lead times the concentration of the chloride minus squared. So what do I do? What is the PB going to be? S, and the chloride is going to be 0.25 squared. So 1.6 times 10 to the minus 5. So I'm taking that, I'm going to divide by 0.25 squared. And I get S, which is the concentration of the lead. I would write that down because we're using the symbol S. Many teachers use X's and there's lots of variables. So what does S actually mean? Now we're using S standing for solubility, but I think they're asking not for the solubility, they're asking for the concentration of the lead, and I get 2.56, 10 to the minus 4. Alright, and then the tough one. First part was the association equation, but now with the BIII, or whatever this is, what is this? It says, if so much sodium chloride is added slowly to a beaker containing silver nitrate and lead nitrate, which will precipitate first, show calculations to support your answer. So basically what you've got is you have a beaker, okay, of some variety. I'm going to just kind of sketch it to give you a picture. And in here we have some lead, and the concentration of the lead is what? 0.15. And the concentration of the silver is 0.12, and we're adding some salt to it. Which could, of course, what do you care about with the salt? The chloride. Which one will precipitate first? Actually, it's 0.1 molar sodium chloride, and you know what? You don't give a rip about the sodium chloride concentration. You just care about these. Because now what you do is, this is where you do like a comparison. You've got PbCl2 goes, notice I've written this like 4 times in this problem. And I'm going to do AgCl. You could do it, you know, in 2 different lines. I think it's good to see it kind of in a comparative. Now, what I know about the lead concentration, it's 0.15, and the silver is 0.12. What I'm going to do is I'm going to calculate the chloride concentration. The lowest one wins. Because we also know the KSPs. Right? The KSP for the lead was 1.6. So I say 1.6 times 10 to the minus 5 would be equal to 0.15 times 2s squared. And then I'm going to take the KSP for the silver, 1.8 times 10 to the minus 10th is equal to 0.12 times S. So now we get our calculators out. Now I'm doing the first one, and I'm not using my solver, maybe I should, but when I get 2S squared to be equal to 1.07 times 10 to the minus 4th. It's actually 4S squared, pardon me, because it's 2 quantity squared, right? So now I divide both sides by 4 and take the square root of my answer, and I get S to be 0.0052. Now, a tricky part about this one, the concentration of the chloride, though, is what? It's 2S, right? So I need to take this one times 2. So the concentration of this one will be 0.0103 molar. That means when the chloride concentration reaches 0.01 molar, you will start making the precipitate. I don't know what this number is, but this is a lot easier. 1.8 double E negative 10 divided by 0.12. This is going to be the smaller one. You get S, which is the concentration of the chloride, is going to be 1.5 times 10 to the minus 9th. Well, this one is clearly smaller than this one, right? So the first precipitate will be the AgCl. Good? Long problem. On this problem, this whole problem, you should only spend 20 minutes. And we just spent probably more than 20 minutes on it just now. Maybe that's about how much we spent. Okay? But you gotta keep through this. Is this helping? Any other questions on 1 through 4?
No, I understand.
Okay, these are hard questions. All right, today our main is to talk acid-base chemistry. Right? So what's up with this craziness on acids and bases? All right, acid-base chemistry. All right, it's not just acid bases; it's acid bases and buffers, and this realistically, guys, I think this is going to be a. Are you going to have a KSP problem on the test? I kind of doubt it. Are you going to have an acid-base problem? I think kind of so. This is a really, really important topic. Okay, if you don't get this question, your chances of a 4 have just gone out the window, kind of deal. Okay, you've got to nail this question, this acid-base chemistry question. Okay, so what's going on with this question? All right, boy, where do you start? There's so much to talk about with acids and bases. What do we know about acids and bases? There's pH, there's POH, acids are sour, bases are bitter, acid-base chemistry. Another couple things about acids and bases. Let's start here. There are 3 definitions of acids and bases, right? There's the Arrhenius definition, and he says acids have hydrogen ions and bases have hydroxide ions. Then there's the Bronsted-Lowry, and he said bases are acids. This is the one that they're bad, right? Bases are acceptors. So bases accept. This is a base right here. Right? I'm doing like a chart here. They accept protons. A proton is an H positive, and acids donate protons. And then there's the Lewis one. This is like the gluon reaction, I like to call it. So the acids accept electron pairs, and in the base they donate electron pairs. Acids are sour, bases are bitter. Some more things about acids and bases. Acids have a pH from 0 to 7, and bases are from 7 to 14. Ringing bells? Okay. This is some just conceptual stuff. We'll get some mathematical questions here just a bit, but let's kind of do some conceptuals. So that's a little bit about acids. That's kind of a good introduction. There's this whole pH scale. Remember, what is pH equal to? The negative log of the concentration of the hydrogen ion. And the POH equals the negative log of the concentration of the hydroxide. Now, if I knew the hydrogen concentration, how could I find the P? If I knew the pH, how could I find the hydrogen concentration? So H positive is equal to what? 10 to the negative pH. And the hydroxide concentration is just like that. It's 10 to the negative POH. You guys remember these things now?
Yeah.
If you take the pH and you add it to the POH, you always get 14. And that's, of course, because the hydrogen concentration times the hydroxide concentration is equal to 1.0 times 10 to the minus 14th. And that's equal to something we call kW. Good? This is just basic review. If you got these if you don't have these down, you're writing them down right now. These are great fodder for a note card. All right, these are memory things. If you have these memorized, you're good. If you don't, make it a note card. And then when you take your note card, go for a walk. Okay, take a walk down the boulevard or on a path nearby your house or whatever you do, and take your note card and start talking to yourself. It may sound weird, and maybe the deer and the elk are going to say, "What's that guy doing?" But you got to memorize some things. What is a good? I have found, honestly, literally, and this may not be you, but I needed to hear myself talk. Sometimes it helped me to memorize things. So I'd have note cards. This is something I did in college, particularly in college, more in college. But I would take my note cards and I would walk around. I'd kind of trying to find private faces because I didn't want them to think I was some weird dude. But many probably did anyways. And I'd walk around and I'd just be talking to myself. And I'd look at the note card and I would say, okay, pH plus POA, whatever it is I was trying to memorize. And then I'd put that note card away. And then I'd pull up the next note card. And that process really does help. And there's just some things you got to memorize. It was great for any kind of test, not just a science test, but for a history test. Now, the science test, we've also got these problems to do. Well, with these problems, of course, the only way to do good on problems is to practice problems. So walking in the woods is not going to help you with that. Memorizing these equations, it will. All right, so you kind of have to. That's the memory trick. But the trick on problems is just to do more problems until you just really have it down. More stuff on acids and bases. There is, if you do a titration with an acid base, right? If you do a titration with an acid base, you typically will take the pH, measure pH as a function of the concentration of, say, the NaOH or something like that. The titration curve will look like this. And what's critical about this particular point on that graph? It's the end point, right? Or the equivalence point. Now there's a very special spot right here too. What's true right here? At half the equivalence point, what is true there? The pH is equal to the pKa. Right? Is that ringing bells? So if you're trying to find the pKa, we did a lab like this. We titrated an acid with the base, and then we found half the equivalence point. And at half the equivalence point, we found the Ka, and we were pretty good. We found the right answer. And that, by the way, is a very potential lab they may ask about. I want to talk about labs here, too. Okay. You could also have a titration, not just with a, that was a monoprotic acid, by the way. You could have a titration with a diprotic acid or a triprotic acid. What you're going to get is you're going to get two inflection points. So you can have a first equivalence point and a second equivalence point. By the way, if this is at 15 milliliters, this equivalence point, this one happens to be at 30 milliliters. I didn't draw it to scale very well. But the second inflection point, if you had a third one, he'd be at 45 milliliters. And the inflection points get a little bit harder to see as you keep going, because the acids get weaker and weaker as you keep breaking up the parts of the polyprotic acid. Okay? And this will have a half equivalence point, and this actually would be where the pKa1 is equal to the pH. Because there was a Ka1, a Ka2, and a Ka3. All right. Another couple of conceptual thoughts about acids and base. If you titrate an acid with the base, if you take a weak acid with a strong base, it's going to look like this, and the pH right here would be 7, but the pH at the equivalence point will be some number higher than 7. Like 9 or 10 or whatever. Why is the pH up here? Why is this greater than 10? No. Why is this greater than 7? It is because the other product of the reaction, what you've got going here is you have some acid, some weak acid HA. It's reacting with hydroxide. Remember, acids react with bases to make salts. And it makes a partner, and you have to make some water. It's going to make HOH plus A negative. But A negative right here, this A negative is basic. Remember, the salts of weak acids are bases, and the salts of weak bases are acids. Ring bell? All right. This leads us to probably the thing that's the most confusing about these acid-base buffer thing. Okay, there are a number of chemicals. Okay, you have reactions, I should say. If I have a weak acid, you have some weak acid HA. It can dissociate, of course, into H's and A's. We're going to kind of work with monoprotic ones and not diprotics for a few minutes. It might take some time for diprotics. But if I have, for example, NaA, where A could be like acetate or fluoride or a lot of different things, lots of things. If I take NaA and I drop it into water, this is actually a good reaction quiz question. The sodium is a Na, so we get to throw it away. The real reaction is not NaA plus H2O. Do not do that. You're going to say what? A negative plus water. But we're going to call water HOH. And it's a double arrow, and it's going to make... Got to make a partner. Who's his partner? HA plus OH negative. That's why this is a base. That's why at the equivalence point, if you have a weak acid, if you're at the equivalence point, you've used up, all you've got is this A negative stuff, but the A negative stuff produces hydroxide, so that's why it's basic. Okay? If I add to a weak acid solution, if I were to add strong base, what would be the reaction? So sodium hydroxide, what would be the reaction? What's it going to react with? Sodium hydroxide, let's say sodium hydroxide, that's the common strong base. What are you really adding? OH, you forget the sodium, don't you? Who's he going to react with? Which of the two partners? And when I say partners, who are the partners in a weak acid? HA and A minus, right? So who's he going to react with? He's going to react with HA. And he's going to make, now this is not a double arrow, this is a single arrow, this is the stoichiometry. He's going to make water, HOH, because you can see the H here and the OH, and it kicks out the A negative. Remember, you got to always make his partner on the opposite side. What if I were to add a strong acid to this system? What's going to happen? What's a strong acid, like HCl or something? What are you adding? What do I care about in HCl? Just the H, right? Good. So that's H positive. Colton, you should write this down. Who's he going to react with? A negative, because that's the base. Acids react with base, and his partner is going to be simply made HA. Now these are going to have numbers and etc. All right, one more thing before we dive into the mathy piece is we can have what we call a buffer. What does a buffer? Let's talk about buffers. A buffer has, what's the kind of the rule on a buffer? What have you got? Significant quantity of both partners. Which means within a factor of 10 of each other. Right? And if you have a buffer, there's a very cool equation. The Henderson-Hasselbalch equation. I'll call it the HH equation. If you have a buffer, you can say that the pH is equal to the pKa plus the log of the concentration of the base over the concentration of the acid. The other thing that's beautiful about this equation, what else is beautiful about this equation? You can also work here in millimoles or moles. It doesn't actually have to be molarity. Because if you're dividing, and the volumes will cancel. So you can just work in millimoles. It's really the only way to do a buffer problem. And actually, while I'm doing this, I realized we just talked about the equations for acids, but we forgot to talk about the equations for bases. So we better problem here. What are the equations? Now, bases they're not hydroxides. It's not like sodium hydroxide. Weak bases always have, well, not always, vast majority of weak bases have nitrogens in them. And so they would be like, let's take CH3, NH2. That's a very common weak base, methylamine. What's the reaction of this? How do I make this a base? When in doubt, react it with water. This is the base, I'm going to call them HOH. Double arrow because this is a weak base. So now, what are you going to make? For sure, you have to make it. It's a base. Makes OH minus. Right? OH minus. Got to say that. What's the other thing you're going to make? CH3, NH3. No, missing a part. Positive. You've got to have charges on this. So the two partners for this chemical, this is methylamine, is this one and this one. Right? Now, if I were to give you methyl ammonium nitrate, or CH3, NH3, NO3, what would you care about in the methyl ammonium nitrate? You would care about this, wouldn't you? You would not care about the nitrate. It's the nitrates. All nitrates are soluble. I don't care if you got methyl ammonium nitrate or potassium nitrate. All right. So if I were to say I have this chemical, you would react it like this: CH3, NH3 positive. You got to put because the nitrate with the negative. And what would you do now? Huh? React it with water. Good. And what's it going to make? Got to make who? Always make his partner. By the way, the word partner, just a good thought here. We're going to use the word partner here, but on the AP exam, do not use the word partner. I invented it, okay? So to speak, in this context. So when we use the word partner, you cannot write the word partner on your test. It's actually the conjugate acid or base, depends. This is an acid, so this is the conjugate acid of this. That's the more precise term, okay? So if you're going to be talking about it in some kind of a verbal discussion, please use the word conjugate acid or conjugate base, depending on which one it is. So you're going to make his partner, which is CH3, NH2, and what's the other product here? H3O positive. Now sometimes we like to do shorthand version. You could also have said CH3, NH3 positive, double arrow, CH3, NH2 plus H positive. Those are the same thing, aren't they? It doesn't matter. Okay, now what if I were to add a base to this? Strong base, hydroxide. Who would he react with? Which of the guys was he going to react with? The base or the acid? The acid. Now, this is the base right here, right? And this right here is the acid. So the acid reacts with the base to make the partner, right? And something else. So you got CH3, NH3 positive plus OH minus. What's that going to make? Water plus CH3 NH2, his partner, isn't it? And if I were to add a strong acid, hydrochloric acid or something like that, H positive, of course that's going to react with the base, so that's the CH3 NH2 plus H positive, and that's going to make CH3 NH3 positive. You see, my experience, okay, as I've watched students do this now for many, many years, 12, I've taught AP Chem 12 years, something like that, is this part of the understanding is the critical thing, the equations. You guys can do the math with your solver in your sleep. It's not hard. But if you get the equations wrong, you get all confused and you get the wrong answers. So this screen right here about these equations, and then the screen back here, this screen right here with the equations for the acid, these are the critical screens. Well, that's not the right screen. Anyways, the acid screen, you know what I'm talking about. Those are the critical things to understanding these problems. So at a particular problem, then we can use those equations, and then the math is easy. It's like, you know, you have an isotable minus x, you have x, you know, x squared. That's not the hard piece. The hard piece is the other. So now let's see if we can find a practice exam. So turn to page 552 in the Barron's. Okay, let's see if, tell you what, I will work you through one problem like this, and then we'll see if we can find another one, and you'll do that. That's how we'll do this, okay? The molar mass and acid dissociation constant of aspirin, acetosalicylic acid, can be determined in a titration experiment. In the experiment, 1 gram sample of aspirin is dissolved to make 500 milliliters of solution. 50 milliliters of the solution is titrated with so much molar NaOH, and the endpoint is reached. Calculate the molar mass of monoproduct aspirin molecule. pH is the endpoint is 7.37. Bunch of information here. Okay. Now, what are we going to call acetosalicylic acid? Actually, not A, but HA. It's a monoprotic acid. The proton is the hydrogen. So that, and what are they doing with this acid? What are they reacting? Read the question again. They're reacting it with sodium hydroxide. So what is this going to be? NHA plus? No. OH minus. We lose the Na. Got it? What's it going to make? Super deep or easy. Water and A minus. Got it? Now, let's write down, like, what do we know? Now, we got a bunch of numbers. We got to get all confused. I know that I have 1.00 grams of the HA, right? You see how the equation is going to make life real easy. It's dissolved to make 500 milliliters, right, in 500 milliliters of the sample. Oh, geez. Then they took 50 milliliters. Do you see what they did? Right, they had a 500 ml, like, volumetric flask, probably, and they put in there 1 gram. Took out 50 milliliters. We don't have 1 gram. We have 50 milliliters, okay, of the HA. And then they titrated it with, the concentration of this was 0.02450 mole per liter. 4 significant digits, wow, and 22.66 milliliters. And the end point is at 7.37, a little higher than what we'd expect. The question is, what's the molar mass? This is harder than most AP questions I've seen. This is a good one. I like it. All right. What's the molar mass? How do you find molar mass? It's grams per mole. Do we know the grams? We got 1 gram, right? So if I found the moles, I'm done, aren't I? That, folks, is kind of the problem. Now, it's at the equivalence point, the end point. That's how they figured this out. So if I have this information right here, the hydroxide, I got a couple information about my hydroxide, I can convert that to moles of HA, can't I? The 7.37 is extraneous information. It might be needed in part B or C. I don't know. I haven't read the part B or C. So let's do this. So they've got a lot of information. So if I've got, what can I do if I've got these two numbers? Find the moles. M times V, right? And we like millimoles. So I'm going to take my calculator. M is 0.0245 times 22.66. I've got 0.555. 0.555 millimoles of OH minus, right? What do I need to know? I don't need the moles of OH minus. I need the millimoles of HA. So it's going to be the same number, isn't it? Because it's a 1-to-1 ratio. 1 millimole of HA to 1 millimole of OH minus, which is 0.555. Well, that's my moles, isn't it? Grams per mole. Now, we do have an if here. Or my millimoles, yeah. But the point here, did somebody see a problem with this? I can't just take 1 divided by 0.555 or 0.000555 or whatever. Why? Because I did not use, how many grams are actually in this 50 ml sample? Can we figure this out? It's kind of, no, this was 500. That's right, it's 0.1. It's a 10% of it, isn't it? So my to find my molar mass, it will be equal to be 0.10 grams, because it's 10% of it, divided by this. Now this does need to now be converted to moles. So if I divide that by 1,000, I get 5.55 times 10 to the minus 4th. Yeah, that's what I got, 10 to the minus 4th. And I get 180. It seemed like a reasonable number. It does. That's A. Usually on the AP test questions, the ones I've seen over like 25 years of AP test questions, they don't make question A quite that hard. Usually it's like find X or something. That is very hard, but it's a level question. That's typically when I see that question, that's like letter C. So I think they probably overwrote it. Not a bad thing if you are prepared for harder questions. Then the easy questions are easier. All right, letter B. Calculate the concentration of the sodium salt of aspirin at the endpoint, and then calculate the Ka for aspirin. Calculate the concentration of the sodium salt of aspirin at the endpoint. All right, so let's rewrite our equation. We had Ha plus hydroxide make water plus A negative. They're trying to find the A negative, aren't they? What's the concentration? Now, we know some things from our previous answer. All right, we had how many millimoles of hydroxide? 5.55, right?
It's 0.55.
Oh, 0.55, all right.
5.55.
All right, here's the easy question. How many millimoles of HA did we have to get when we got to the equivalence point? 0.555. By definition, the equivalence point is when the moles of the acid equals the moles of the base. This is an ice table, right? So this becomes minus 0.55. That's 0. Minus 0.555. 0. How much A negative did we start with? 0. So plus 0.555. It's 0.555 millimoles. Now they asked for the concentration, right? So the concentration of A negative will be 0.555 millimoles divided by the volume. Now what will the volume be? Think about this for just a moment. It's a little tricky. 50 is incorrect. It is 72.66 milliliters, because remember you put 50 milliliters and you added 22 milliliters. And you can take millimoles divided by milliliters, and then your millis cancel, if you will, right? And so what does somebody get on that one? I don't have a calculator on that one. Maybe somebody else can get that one. There you go. That wasn't a bad question. But it assumed you had the answer to B, didn't it? If you didn't, make up a number, right? How would I do that if I didn't know the number? Probably this one, actually, you didn't have to know the answer to the previous one, the molar mass, but you could do this actually independently, couldn't you? If you took M times V and just write out the reaction. But notice, if you got this, don't have that reaction, you're basically hosed. All right, letter C. Oh, wait, what did we forget to do on B? It says also, and this is an issue, it says calculate the Ka for the aspirin. Now, pH at half the equivalence point, we do not have a graph, so we're not able to do that. I know how to do it. Okay, I just thought of it. You'd have to, okay, this is hard. All right, you take A negative. I may be wrong on this. I'm going to kind of work it out in my head here. It makes HA plus OH minus, right? We know this right there is 0.00764. Oh, I know how to do this, yeah. Right? That's the concentration of the A negative. What's the concentration of the hydroxide? No. We know the pH is 7 point something. 0.37. So the pOH would be 14 minus 7.37. It's 6.63. So the concentration of the hydroxide ion will be 10 to the negative 6.63, right? So 10 to the power negative 6. I get the hydroxide concentration to be 2.34 times 10 to the minus 7th. What's the HA concentration going to be? Same number. because when it breaks apart, it breaks into one of these and one of these. So this is also 2.34 times 10 to the minus 7. Wait, well, no, that's not the answer. Well, I still need to find the... I can find... Now, this is tricky, because they didn't ask the Ka. This is a hard question, my word. You need to find the K... We can find the Kb. The Kb... All right, I'm going to need the page here. The Kb... No, because that wouldn't give you Ka. It's going to be the concentration of the Ha times the concentration of the hydroxide. There might be an easier way. I don't know. I mean, over the concentration of the A negative. And this is going to be 2.34 times 10 to the minus, was it 7th, I think? Squared over 0.00, what was that, a 7 number? Somebody got it written down. 764. So when I get that number, I get 7.19 times 10, that's a 9, times 10 to the minus 12. That's the Kb. What's the Ka? Remember, we can write this, Ka times Kb equals Kw, and Kw, of course, is 1.0 times 10 to the minus 14th. So we're going to take 1 to the minus 14th, divide by 7.19, double E minus 12. Boy, that was ugly. Alright, so you take the Ka will be 1.0 E negative 14 divide by 7.19 E negative 12, and that equals 0.0013. So 1.3 times 10 to the minus third. Boy, these questions are harder. This question is harder than an AP exam question. It truly is. And if I'm not mistaken, you can look in the back and Mr. Barron has got this answer worked out. In fact, I just looked. I saw it. I mean, not particularly, but I just saw answers. Letter C. Now, I like this. Using the Ka from Part B. Now, if you didn't get the Ka, because that was a tough question, make a number up. 5.4 times 10 to the minus third. Pick a number. I don't care. 10 to the minus sixth. All right. For what pH range can aspirin and its sodium salt be used as a buffer? All right, the Ka is equal to what? 10 to the minus third, right? Ish. You know, I'm just going to be now roughly. So what range is it going to be a good buffer for? Plus or minus 1 of the pH. So what's the pKa? Let's actually just find the pKa. It was 0.00139 was the Ka, right? Or wasn't that what it was? So let's take the negative log of that. Negative log of 0.00139, and I get 2.85. That's the pKa. It's perfectly a base at 2.85. So I would say from 1.85 to 3.85. That's where it's going to be a good buffer. I don't think we've ever talked about where's a good buffer range. Find his pKa and then add 1 and subtract 1. If the sodium salt of aspirin is written as NaA, write the hydrolysis reaction for the sodium salt and determine its equilibrium constant. We already did that. Didn't we? Letter D. You're going to just take A negative plus water makes Ha plus hydroxide, and they're trying to find the Kb. But we found the Kb to find the other problem. There might have been an easier way in letter C. I hadn't really thought through. That's the way that's in the brain there, if you will. In letter C, we found the Kb, didn't we? That's right. 7.19. That's the number right there. So the number is 7.1 to the minus 12. So we found that. Wow, that was truly an ugly problem. Let's talk about lab issues here now. If they ask you a question, this would be a separate question, a lab question regarding an acid base, since that's our topic for today. What might they ask you? Okay, basically it's, be like the labs that we've already done. All right, there are probably two different acid-base labs that they could ask you about. Number one is actually the question that we did with Mr. Barron just a minute ago. They may ask you to calculate the molar mass of a weak acid. All right? How would you do this? Well, it's like Mr. Barron's. You're going to have some acid, HA, and then you're going to have some sodium hydroxide that you have standardized. Now, I'm not thinking you found his concentration. So the question is, what's the molar mass of some acid, HA? You'll be able to weigh out the acid, right? Like the problem just a minute ago, you had 1 gram of the acid. I'm just going to make up some numbers. But you're going to have to be able to describe the process. And then you're going to have, you know, a burette, and you're going to titrate it. You're going to titrate the sodium hydroxide of known concentration. So let's say I know the concentration. Sometimes I think it's not a bad idea on these lab questions, even though at this point you will be without a calculator. It wouldn't be a bad idea to make up some numbers. Make up, right, nice, easy numbers like, let's say, 1 molar, okay, good, and 10 milliliters or whatever. If you want to make up numbers and do a sample problem for them with easy numbers, then you can do this. How would I find the molar mass? Well, M times V gives me moles. I then can convert moles of this to moles of this, take the grams divided by the moles, and that's the molar mass. Right? Now, we didn't do a lab like this. We did a different type, but that's the second kind. But just think about it, and I think it's a good idea to, when you have these problems, they tend to be mathematical labs. But you don't have a calculator, and they're not making you calculate the answer. They would want you to describe how you would find it. But the basis of all these labs is some calculations. So I think it's wise, even though sometimes, and I've never completely liked some of these questions, sometimes it seems like they ask the calculation piece like in part C of the question. And I think that's not the best call. But reality is where it is. And so I think it's best to do the calculations first. Then they might ask, for example, what happened if you overshot the endpoint? What would happen to the molar mass? And you know, we've done titrations where it becomes too pink with phenolphthalein or whatever. What would happen to the molar mass? Remember, molar mass is the grams divided by the moles. Which of those numbers would change if you added too much sodium hydroxide? And would it become larger or smaller? It become larger because, see, your volume, you're supposed to get 10, but you go to 11. Well, M times V now becomes a bigger number, so it's going to cause your molar mass to experimentally be too small. It's a reciprocal deal, isn't it? Does that make sense? What happens if when you poured some water into the when you poured your sodium hydroxide into the burette, your burette was wet? So you have a wet burette. So you had little drops of water in your burette. What would that do? The concentration of you're assuming it's 1 molar, but you've actually got like 0.9 molar, right? And again, I think it's not a bad idea to make fictitious numbers up. I think it makes more sense to students. So you'd say, well, it's 0.9. So when I multiplied 1 times this, I still got whatever number, but the stuff I really had was 0.9. So that's going to make your mole number bigger than it's supposed to be. So therefore, it's too big. It actually should be smaller. So your number, actually, this is going to be a big one too. This is going to give you too big of a molar mass because the mole number is too big. This is a little bit weird. Okay. This is what you've measured. 1 times 10, right? 10 millimoles. You had 10 millimoles. But the reality is you did not add 10 millimoles. You only added 9, right? Because this 1 molar was too high a number. So you actually added 9. Since you added 9, I don't know. Let me think about that. Yeah, it would make your moles too small, which would make it's going to make your moles too small, which means your molar mass higher. The opposite of the previous one. They're going to ask like some error question. They love to talk about error. I mean, describe the calculations. What measurements would you need to make? Describe the experiment. What would be a procedure? Real quickly, those are the kinds of questions. Design an experiment that would do this with these 5 pieces of equipment. A burette, some standardized sodium hydroxide, something like that. Okay? They might even, boy, just ran out of time. 10:44. You know, I might remind me that there's one more type of acid-base problem I should chat about, and I can do that at the beginning of class next time. We got like 40 seconds. There's no way I'll get to it. So